So in this lecture, we're going to cover the relationship between fluid pressure and velocity, essentially Bernoulli's principle. So as pressure increases, velocity will decrease and vice versa of liquids and gases flowing through channels, ducts, and containers. So we can actually describe the relationship between fluid pressure and velocity by using this equation here. Pressure is equal to 1/2 fluid density rho times the fluid velocity squared. So we'll use two examples, one focusing on airflow and another focusing on water flow. So if we define the components of the equation, we have those units measured and calculated in metric units, but we'll explain the relationship between fluid pressure and velocity with respect to the US units of measurement. So if we were to measure pressure in the metric system, it would be in pascals. And so then we have its relationship to pounds per square inch of the US system. And then the density of water, 1,000 kilograms per cubic meter. We can convert this to its pounds per cubic foot density value. So you can either use a table or a Google calculator or just manually convert it mathematically. So we get 35.29 cubic feet to a cubic meter. So when we divide these out, we get an approximate density of water at 62.34 pounds per cubic foot. We can then convert meters per second velocity to feet per second. And then fluids include all liquids and gases. So again, we take this equation, the relationship between fluid pressure and velocity, and we isolate it with respect to water and solve for the velocity component. So we just substitute and solve. So we know if we have 1 psi of pressure across some side of a duct, we'll say the input side, we're going to harness a 12.17 feet per second differential. So we'll explain that in a second, but it's actually a faster way to do fluid dynamics and computational fluid dynamics by getting the differentials of the liquid substance or gaseous substance, fluid substances you were working with. So in this case, we're just going to isolate the differential for water and air with respect to pressure and velocity. So we're just converting the average air's average density from its pounds per cubic foot value to its kilograms per cubic meter value. So these are all just values you can look up or calculate manually. And so we get the pressure velocity differential for air. And this comes to 1 psi is 353 feet per second. And these are, of course, density specific because obviously the densities of air and water are vastly different. So next we have to add the continuity equation, and this then completes the total relationship understanding. So if we had a duct with a compressor fan ingesting airflow and compressing it through the duct greater than atmospheric pressure, assuming the fan has the power to do so, we would incur obviously a backing pressure. So this sort of pressure is known as static pressure, but the pressure while the fluid, or in this case air, is moving is known as the dynamic pressure. So assume the fan is maintaining a consistent input velocity of air ingestion of 3 feet per second, and the intake is 4 inches in diameter, and then the output is 1 inch diameter. We'll call that the A1 and A2. So we have to actually use the diameters to solve for the cross-sectional area. So we use pi r squared. So in this case, we'll just calculate the square inch cross-sectional area of the inlet. So we get 12.57 square inches, and then we can just convert it to its square meters cross-sectional area. And then we do the same for the area 2. So that's 1 inch diameter divided by 2 squared times pi. We get 0.785 square inches. We find its square root. To get linear inches, divide that into 12 for feet, and then divide that into 3.28 for meters. Then we square the calculation, and we get 0.0005 square meters of cross-sectional area at the outlet A2. And so again, we can convert the feet per second on the inlet from 3 feet per second to 0.914 meters per second. And then we solve for, in this case, V2. And so when we solve for V2, we just take the A1, 0.0081 square meters, times V1, which in this case we calculated the inlet velocity is 0.914 meters per second, and then we divide it by the cross-sectional area of the outlet, and that's 0.0005 square meters. So we get 14.8 meters per second, and we convert it back to feet per second. So 48.5 feet per second is our V2. So the air goes in at 3 feet per second, and it discharges out of the outlet at 48.5 feet per second. So this is where we can use our differential and just simply divide the outlet velocity V2 into the 353 per 1 psi differential and multiply that times psi. So then that gives us the P2 output pressure at 0.137 psi, and that is dynamic pressure. And we do the same thing for the inlet, 3/353 times 1 psi, and we get 0.0085 psi on the inlet. So the inlet has a lower pressure than the outlet. And then if we check our work, we can also use another method, and that's by calculating the pressure ratio. So all we do is divide the A1 over the A2. So that is a typo. I'm going to have to flip that around. So the A1 is the inlet. So I'll fix that in a second. Divided into the outlet cross-sectional area. So we have a pressure ratio of 16:1. So if we convert 3 feet per second velocity at V1 to the output velocity, we can just multiply the inlet velocity of 3 feet per second times the pressure ratio, and we do calculate 48 feet per second approximately. So that's another way to solve for the outlet velocity and or check your work. So that's been proven as correct. Remember, I'll fix the pressure ratio equation in a second here. So as fluid pressure decreases, fluid velocity increases. So this is Bernoulli's principle. And so pressure represents the potential energy and also the mass. We have more mass moving at slower velocity, so it's pressure dominant. And then the velocity is the kinetic energy, and that represents the conservation of energy the total energy is equalized as the cross-sectional area narrows. So we're not changing the energy, we're just increasing the velocity to keep the total input-output energy at zero, including friction losses, of course. But if we exclude that, we have then the equilibrium, and this then obeys the first law of thermodynamics, which states that energy cannot be created or destroyed, but only change in form. So this ends part one, focusing only on airflow with respect to the relationship between fluid pressure and fluid velocity. So we'll clear this one out and then start with part two, which is the water portion. So again, let's say we're dealing with a boost pump and it is connected to some sort of a water head, and it's a positive displacement pump, so it's pushing the water at a pressure greater than atmospheric pressure. So call this water pump. This is positive displacement, so it's pressure pushing rather than a vacuum. It is a positive displacement pump. And so let's say that pump has a 40 psi gauge pressure rating. It goes into the head, has a 4-inch diameter inlet, and then a 0.75 inch diameter outlet. So we don't have any data on the velocity on the input and output. We only know the diameter on the inlet and the diameter in the outlet. So first step, we can solve for the V2. But it's easier to just find the pressure ratio. And so we're just going to convert the four-inch diameter intake into the square inches cross-sectional area, and then convert that to square meters cross-sectional area like we did before, except I'm just going to convert that should be A1 right there. So I'll flip that around in a second. So yeah, 4 inches divided by 12 feet divided into meters. So we get a 0.102 meter diameter. And then we just use pi r square and we calculate 0.0082 square meters. So again, our pressure ratio is A1 over A2. So we take our A1, divide it into our A2. So we get 28.9 to 1 pressure ratio. So if we divide our 40 psi inlet pressure into 28.9, we calculate 1.38 psi dynamic pressure on the outlet. So then we can access our differential, our pressure velocity differential for the water applications, And so if we take 1.38 psi and multiply it times 12.17 over 1, we'll calculate 16.8 feet per second at the outlet. So then we can just simply solve for the V2 using the continuity equation, or we could also use that into the dividend of the pressure ratio. We could divide it into there, but we'll just stick with a continuity equation. So if we solve for V1 algebraically, we get A2 times V2 divided into A1. So again, our V1 inlet velocity is the cross-sectional area at 2 times V2 divided into A1. So we calculate 0.18 meters per second, and we convert that back to feet per second, 0.6 feet per second. So if we want to check this, because we could have also just divided that into the pressure ratio, we would have got the same value, but we'll use the pressure ratio as the test check. So if we multiply 0.6 feet per second times the pressure ratio, we get approximately 17 feet per second. That includes the rounding error. So you can use both. You can divide one velocity component or multiply it or divide it into the pressure ratio. And of course, if it's a convergent duct like this one, the cross-sectional area is getting narrower, so it's convergent. But if it was going the other direction, if it was divergent, the water was flowing from left instead of from left to right, but right to left the other direction, then you could divide it into the pressure ratio because the velocity would decrease and the pressure would increase. So again, you can use both methods. Use the pressure ratio as the dividend or multiplier depending if the duct is constricting or augmenting. So we call P2 as 1.38 psi gauge pressure. P1 is 40 psi, and then we have V1 0.6 feet per second, V2 16.8 feet per second. So if we study the calculations, we can prove that Bernoulli's principle is indeed, as pressure increases, velocity decreases, and vice versa. And so then we have to also just touch upon the static versus dynamic pressure. So the pressure while the fluid is in motion is the dynamic pressure, and the static pressure is the resting fluid pressure. So if you have a gallon of water inside of a jug and you lift the jug up, it has static pressure. Or if any fluid, air, and liquid is at rest, it's going to emit static pressure anyway. And in the case of the jug, whether it's on the countertop or you're lifting it, it still has a static pressure. Nothing's actually moving. But if you open up the cap and pour, or tip it upside down and open up the cap, you notice that the water doesn't all instantly come out because only so much can come out based on the constriction. And so there is some backing pressure, and so that would qualify as static pressure as well. It's very low. So if you had a pressure gauge, static and dynamic on the gallon of water, and you open it up, before opening it up, the dynamic pressure would be 0, static pressure would be maximum, and then you open up the cap and then you'll see the static pressure suddenly drop, but not go to 0. It'll be a little bit there, but then the dynamic pressure will be surging until it stabilizes. So we could just also describe static pressure as backing pressure, but the pressure incurred during motion is the dynamic pressure. So this ends part 2 of 2, and I will end this lecture with a few notes here. If you're also needing to calculate the friction losses of water through a pipe, you can use the Darcy-Weisbach equation. In this case, fluid as in water, friction losses through pipes only. Thank you for watching this lecture, and have a great day.